So what a logarithm is an inverse function of an exponential function. So from the previous recordings and handouts, we know that if we have a constant, say a bigger than 1, then the function f of x is equal a to the x. That can be represented as an increasing exponential function that is asymptotic to 0 this way and goes to infinity that way. And we know that this point here is the point 0, comma 1, because whatever a is, when I raise it to the 0th power, I'm going to get 1 as the output. Now, the inverse function of any function simply reverses the roles of the inputs and the outputs. And we know that this function will have such a function because it's one-to-one, right? No two inputs will give you the same output. Every output is unique to the input. And so if I take this curve and I reflect it across the y equals x line, i.e. I switch the role of inputs and outputs, what I end up with is something like this. And this function is the function g of x equals log base a of x. And we can see some of its properties here. It goes up to infinity this way, so it goes up to infinity but slower that way. It's asymptotic to x equals 0 or y equals 0 here, so this is asymptotic to x equals 0 here, and this point here is 1, comma 0. So would log base a, if you take log base a and I plug in x, what I get is a number, and that number is the number such that if I take a and raise it to that number, I'm going to recover x. Right? So it's the inverse of a to the x. It undoes that process. So for example, log base 2 of 2 is 1, since 2 to the first is 2. Log base 2 of 4 is 2, so 2 to the second is 4, and log base 2 of 8 is 3, since 2 cubed is 8. And so seeing something like that might help clarify the shape of the curve as well, since we see here, right, that 2 to the 0 is 1, so that's 1, and then I have to go forward just by 1 to get another 1, so this is when x is 2, y is 1. But then to go up by another 1, I have to go all the way out to 4. And then I have to go forward all the way to 8 to go up by, to get to 3. And then I have to go all the way out to 16 to get to 4, and all the way up to 32 to get to 5. So we can see this thing is increasing, but it's slowing down as it rises. And so that gives us this curve that rises, but it rises slowly, right? It doesn't rise like a straight line. It's stretched out in this way. This inverse relationship between the log and the exponential also is what gives us our two fundamental kind of log arithmetic properties. So one of our properties is that for any log base a of, let's say, x times y is equal to log base a of x plus log base a times y. And in order to see why that is true, remember that this is an invertible one-to-one function, and so two things are the same if and only if their inputs are the same. So we also know that this thing is the inverse of the exponential function. So if I compose it with the exponential, those things will cancel each other out. So what we know as a to the log base a of xy, those cancel out, and I just get xy. On the other hand, a to the log base a of x plus log base a of y is equal to a gloss base of x times a log base a of y by standard exponent rules. This thing, the a and log a cancel and gives us x. This gives me y, so I also get xy, and so this and that must be the same thing. There's a similar, I'm going to erase this, rule for products or for exponentials. So log base a of x to the y is equal to y log base a of x. And we can show this in the same way. A to the log base a of x to the y just gives me back x to the y. Now a to the y times log base a of x is the same thing as a to the log base a of x to the y. This thing cancels and just gives me x to the y. Now, maybe to see some examples of these facts, let's compare log base 4 times 8 and compare it to base 2 of 4 plus log base 2 of 8. Log base 2 of 4 times 8 is log base 2 of 32, which is log base 2 of 2 to the 5th, which is 5. All right. Whereas log base 2 of 4 is log base 2 of 2 squared, and log base 2 of 8 is log base 2 of 2 cubed. That gives me 2, and that gives me 3, which gives me 5. And so there's nothing really crazy being said here. All that's saying is the power that I need to raise 2 to get 32, that's the power I need to raise to get to 4 plus the power I need to raise to get to 8. And this is no different here. Let's compare log base 2 of 4 cubed. I compare that to 3 times log base 2 of 4. Well, log base 2 of 4 cubed is log base 2 of 64 if I cube 4, which is log base 2 of 2, 4, 8, 16, 32, 64 of 6. 2 to the 6, rather. And 2 to the 6, well, what power do I have to raise 2 to get 2 to the 6? That's just 6. Whereas here, 3 times log base 2 of 4 is the same as 3 times log base 2 of 2 squared, which gives me 3 times 2, which is also 6. So we can see that these things coincide. So generally, if you have a log base something, most numbers are not a clean power of that base. And so you're not going to get a nice whole number as a result of that computation. It's going to be some weird thing. But that's what technology is for. The calculator and Desmos helps give us precise answers to things that are hard to work out by hand in such a way. And so this helps us. One of the big reasons we use logs is to de-exponentiate problems. So, or expressions rather. So there's a special type of log, log base E, which is called the natural log, denoted ln. And so I just wanted to know, what if we want to solve something like, uh, what do you have to raise 2 to get 5? So clean powers of 2 are things like 2, 4, 8, 16. 5's not one of them. But presumably it should be something between 2 and 3, right? 2 squared is 4, 2 cubed is 8, 5 is in between. Well, we could find this by taking the natural log of both sides. And on the left-hand side, we would get x natural log of 2 is equal to natural log of 5. Therefore, x is the natural log of 5 divided by the natural log of 2. And then these values you can compute in a calculator. And this expression here, you can compute in a calculator. And that's something that you could then express the answer of. And so a lot of problems potentially have unknown or unsolved things in the exponent. And by using the natural log, we're able to take those things and bring them out, and then we can apply the standard algebra to what remains.